Thank you very much for your kind introduction. And also I should thank the organizers to invite me to this meeting. I feel honored to be still part of the younger generation. Darius smiles, and he knows why. I know why he smiles. Anyhow, let me first start with a nutshell picture, basically. Eva was already onto the same topic today. So basically what we do is we use a high energy photon, or it could be also several photons. We could do a few photon excitation of a molecular system, and what we are really interested in are the process where not only one electron comes out, but two or more, like Bremsel was talking about yesterday, double O'Shea and so on. So this is about the electronic structure. And then, of course, if you do it in a molecule, things may change. Nuclear dynamics occur, fragmentation, and so on. So this is basically what one of the main themes are in my group. And what I will speak today, what I will focus on today, is the question of basically, isomerization. I think isomerization processes in molecules, they have been studied up to now quite a lot in neutral and singly ionized systems. But if you look into the literature, it's not so much known about isomerization processes in doubly or more highly ionized systems. And I come up with a little bit of a claim. I say it could even be that they are actually the rule rather than the exception, but we will see about that. Okay, so now what I really would like to do is first of all introduce you to the technique which we use, how we get the spectra. And this is invented by a person Silma mentioned yesterday, John Eland, Oxford University. It's a story which has been going on for quite a while. It's still one of the strongest techniques on the market to do it. It's called the magnetic bottle. And the basic idea is that you have your gas sample coming in, and the light crosses it, and then you create the electrons and the ions in this light matter interaction point. Use a strong magnet close to it, and the idea of this strong magnet is basically to make sure that the electrons which you generate, they go all in one and the same direction, go into a long flight tube, a few meters long, and then we have a detector at the other end, and what we basically measure is the time it takes from the point where the electrons were born until they reach the detector. We use this is classical mechanics, right? This is the kinetic energy. You know basically the travel distance, and then this way you can work out. You measure the flight time, and by using this simple relation, you can work out the kinetic energy. It requires pulsed light sources. Originally, we used pulsed helium lamps. Then it was transferred to synchron radiation, and more recently, people actually like it also at free electron lasers and high harmonic generation at the second science, and this also things there. So this is just a textbook example of how we really get to the electron spectrum of a doubly ionized system. We measure the arrival time of one of the electrons. We assume it comes before the other, so flight time of one versus the other. And the point is that those electrons which are originating from the same molecule or from the same atom, they give rise to distinct features in what we call then the coincidence maps. We convert it from the flight time scale to the energy scale. Those hyperbolicas, they get straight, and then we sum up the intensities along the straight lines, and we arrive at a spectrum which looks very much like, and it is an electron spectrum, but it's an electron spectrum which reflects the doubly charged system there, the dicationic electronic states there. And you can do a little bit more. You can actually plot it in a three-dimensional way. And so this is basically now done here. It's replotted. And the point why I bring it up is that when you look at it in a three-dimensional way, you see that there are sharp features, but there is also continuous background. And this is basically what Bremsel was on yesterday. The double ionization processes, they can occur either in a sequential way, or the two electrons can come out directly and share the energy continuous. And those who share the kinetic energy continuously, they will give rise to this continuous background. And the sequential processes, they are imprinted on the sharp features. So you basically have the two electrons which are ejected, they come out with well-defined energies. This is how we can distinguish those processes. Now, in order to not only measure the electrons, but the ions, we need to detect the ions, and there are different ways of doing it. This is the first version of what Elon and I developed at the time. There are different versions around, but this is a nice way of doing it. Electrons in one direction, and then you make a hole in the magnet so that the ions go into the other direction. And in this way, we can get the complete picture of the ionization processes there. Now, there are a bunch of spectrometers around, and they're used at various places. So if someone is interested in, I'm happy to talk about it. We have ourselves, we are operating by now actually 5 of those. I will skip this now and go on to the SO2 result, which is basically what I want to focus on. So the double ionization of sulfur dioxide. And I want to start off with what we call the electron pair-only spectrum, or the electron-only spectrum. This is what is shown here. And then, of course, to make sense out of the features, we need theoretical support. And I will come to the theoretician who helped us in assigning the spectra in a minute. So this is basically the electron spectrum. We can see here, for instance, there is a state, or there are states with vibrational substructure. And then you can add on the ion information. The resolution on the electron side gets a bit worse, but what you actually gain is you can decompose this electron spectrum of the dication into how it fragments actually. So you see that certain parts of this dication ionic electronic spectrum will lead to, for instance, the formation of an SO2+ species. So it's a charge retaining process. The double charge remains on one of the fragments, and a neutral oxygen atom has gone off, which is a sort of interesting process in itself. Then there is another, the sort of thing which naive thing of thinking about how SO2 may dissociate is O plus SO+, so we clearly get this as well here. And then on the other slide here, I will actually show you one channel, which is the one which I think is very interesting. We find actually the formation of O2 single plus, so molecular oxygen singly ionized. If you think about the SO2 molecule, in its neutral form, the sulfur atom is in the center, and you have the 2 oxygen atoms out there at the terminus. So then you can ask the question, how does the system can go to a fragment like O2 plus if in the neutral phase the sulfur atom is in the center? So, and one point which is quite important now for the remaining part of my presentation is the energy, the onset of this formation of O2 plus. It's around 35.5 eV. And in order to get an understanding of it, we of course need to get also theoretical support. And in this case, we got the theoretical support of Max de Hoekla from Paris. He came to us to Gothenburg during the pandemic, and this is where we could focus on that particular approach. And the idea which Max came up with at the time is actually to first of all look at the potential energy surfaces of OSO++, and also actually think about isomerization processes, so OOS++, for a wide range of nuclear configurations. And the first thing he and one of the students did was calculating the ionization energies in the couple cluster level. And so in the doubly ionized ground state, the geometry looks like this, and the lowest ionization energy is about 33.33 electron volts. And then there are excited dicationic states where the geometry is bent. And then the idea was, of course, to first of all, look at this in more detail. And this is then what they did. They calculated the potential energy surfaces using the CAS-CF method. to calculate the total energy for a certain geometry. You know, it's a very tedious sort of work, vary the position of the sulfur atom, both in terms of the bond distance and the theta, relative to the center of mass of the molecular oxygen. One uses the reduced Jacobi coordinates for that. So there are the results for the case where one assumes a geometry like this, so the angle theta nearly 90 degrees, so the sulfur atom basically being perpendicular to the O2 part. And these are the potential energy curves one can then get by varying the distance of the sulfur atom relative to the O2. And what we can see in this case is that the energies out towards the dissociation, they are by far too high. They are not in the ballpark of 35.5 electron volts. And then, of course, we realized, okay, it's not going to be like that the sulfur atom flies away in this direction, and in this way O2 single glass is formed. So then they went on and did many more calculations, started to vary the angle theta, and again varied the bond distance of the sulfur atom. And they use this concept of minimum energy path. So basically one selects the lowest energy for each R of the sulfur atom as a function of theta, and then one creates their one curve per symmetry spin. And this is then the results which one arrives at. And the interesting point is there is, first of all, there is a minimum out there which corresponds to the one of the excited states of the doubly charged SO2 molecule, which is spent. But then there was a second minimum even further out at a longer bond distance. And this turned out to be then actually related to having the OOS geometry. It turns out to be metastable, and to get it there, of course, this is a kind of living process. Then they went back to the couple cluster calculations, and they could confirm also the ionization energy of this state there, which fits very well. And then the next question was the state selective dissociation. You know how to get there, and it's again the same sort of concept there. One uses a minimum energy path, and what they find then is basically that the sulfur atom in this sort of geometry here will leave the O2 plus behind by overcoming a barrier, and it goes from one state into the other. And it's then actually the fragments which are created, the sulfur atom will not be in the ground state, the sulfur plus atom, it will be in an excited state. So now you can ask yourself, why is this interesting? And this is why I had this more sort of perhaps catchy title there at the beginning. If you think about molecular oxygen, we all know it's necessary for life and is accumulated in Earth's atmosphere since about 2.4 billion years ago. If you look at it more carefully, then you realize that the abiotic origin of oxygen is still not fully established. The numbers are not coming together there. The common models, they involve primarily CO2 or water vapor, but the amounts are not still not coming up there. So our suggestion, this is what we put into this paper here, is that there could be additional and perhaps even somewhat significant contributions from sulfur dioxide rich environments, like for instance planetary atmospheres, Jovian moons, Io, Europa, and Ganymede. This is basically the idea of this paper. And then when we submitted the paper, we were asked by a referee to come up with an estimate on how likely this actually is. So we went back. We started, first of all, we did it for a series of photon energies. This is 41 eV, which we have in the lab, and then into synchrotons. So we get the fractions of this from our measurements. And now in order to estimate how likely the whole thing is, use cross sections at the relevant photon energies which are in the literature. We assume a vertical distribution of SO2, that we assume that it can be represented by a single 1 centimeter thick layer, and we use estimates of solar XUV fluxes, and what we then actually found is a rough estimate is about 2% of SO2 is converted to O2 single glass per year, So it means basically if it would not be replenished, then after 50 years the whole thing would be gone there. The next question is then how to actually get from O2 single blast to neutral O2. One idea might be that might be this electron recombination, and this is what Henning shakes his head. And this is true, of course. Free electron typically dissociates O2 single blast, so this is not the answer. But the answer we believe is then that there is charge exchange going on right in the atmosphere, and you look at the basic ionization energy of oxygen and look at which other systems are out there which have ionization energies close to or lower. And we think that primarily it could be NO in the present atmosphere, but there are also other systems which could contribute to this sort of charge exchange there. So this is basically the story I wanted to go through here now this afternoon. How, by doing this sort of double ionization, going through double ionization, how one possibly could get to neutral oxygen molecules, the neutral oxygen molecules. I should say that we are not the only one, and I was very surprised to see actually in the February edition of Science an article which is very similar. The experiment is somewhat different. They use a few photon excitation, but they look at SO2. They found the same pathway, double ionization, and the theoretical part is very, very similar to what Max de Hooggraaf was doing it. What they haven't done is, and I feel a little bit offended by that, I have to say that, is they didn't want to cite our paper. Anyhow, no hard feelings really. I want to end up by just giving another example of double ionization, another molecular system which I find is very interesting, the alene molecule. So 3 carbon atoms, and then you have above the terminal ends, you have 2 hydrogen atoms there. We did again the double and triple ionization of alene. Is the work of one of the students in my group. And then we looked at the fragments again. And if you look at here, you could find H3 plus. And in order to get H3 plus from alene, one of the hydrogen atoms must move to the other side and form it somehow in the double ionization process. So this is why I say this sort of isomerization things. I believe we have other systems where we also see peculiar things. I believe it's not the exception. It's probably rather the rule that these sorts of things are actually happening. And for this, there is actually a theoretical prediction out there for this channel. So they predict that this should occur on a sub 120 second time scale, but there is no time resolved experiment. By this, I will just stop here. I thank you for your attention, and of course I want to acknowledge people working close to me. John Leland's still around on an advisory basis. This is the group as the group looked like a few months ago, 2024, and we have another activity which is coming up there, which is a new laser. Thank you for your attention.
Thank you, Raimund. It was a very nice presentation. Any questions?
Thank you, Raimund. Super interesting. So, I was wondering actually about the coal process in a planetary environment.
Mm-hmm.
So, have you thought about? Well, this is something I don't know, but maybe you considered that about the flaring of stars. So, I know that especially young stars, they flare quite intensely at around 210 nanometers, and sometimes you get very high intensity. I don't know if they flare at higher energies, but then the question is if you get high intensity, maybe you could also get the same process via some multiphoton ionization. So where I'm going is, I'm just wondering about an environment which might be not in our star system, in our stellar system, but somewhere else, where you could actually generate a lot of oxygen from SO2, which could be possibly observable from a telescope, like with JW's team, and then get it a lot in the short term with some multiphoton processes.
So no, we haven't thought about it, to be honest. But I find it's very very interesting, and I also believe that I mean there will be areas out there where photon intensity is very high, so that actually few photon or multi-photon cases can occur. And the other paper which I mentioned there at the end, that science paper from February 2024, this is a few photon study experimentally, so definitely yes, you can definitely say so.
Question about this reaction, like how to get from oxygen cation, let's say, to neutral oxygen.
Mhm.
My question is, what about negative elements?
Uh,
Yeah, there should be in cloud something, yes?
Yeah, could be another possibility, right? And then, of course, the electron, the additional electron on anion to get off is even easier than from a neutral system. Yeah?
Yeah, but do you have idea what kind of an ion it could play a role in atmosphere? Or we should check in the literature.
Yeah, I think so. Yeah, it's definitely. It's
Okay. Last question. Still have some. Okay, so thank you, Raimund, again. Thanks all for all the speakers.